So there are 3 questions. If you can simplify them, and then we'll discuss maybe why. Well, you might be able to think about why I've given you these questions when we eventually get the answers.
I've done the questions.
Awesome. Okay, so we'll go through some answers then.
For the first one, I got 2.
Hold on. Let me. Okay, so for the first one, you got. Yep, you said 2. Uh-huh.
The second one, I got 16.
Okay, so just going through this, that is square root 16, 8 times 2. 8 times 18 is 144. So square root 144. Square root of 16 is 12. That's wow. My mind is just way too far ahead. The square root of 16 is 4, and the square root of 144 is 12. And altogether that gives you 16. Yep.
The last one, I got 1.
Okay, so let's see. So 2 times 2 gives us 4. 2 times root 3 gives us plus 2 root 3. Minus root 3 times 2 gives you minus 2 root 3. And then minus root 3 times root 3 gives you minus 3. And then simplifying, the 4 minus 3 gives you 1. The 2 and the minus root 2. Sorry, the 2 root 3 and the minus 2 root 3 cancel. So it's left with 1. So why do you think I gave you these third numbers, these questions?
I'm not too sure.
Well, the kinds of questions that I gave you, they had surds in them, but what about the answers?
The answers are whole numbers.
Yeah, they're whole numbers, or in other words, they're rational. They don't have whole numbers. Well, they don't have surds. Yeah, so they don't have surds in them at all. So, that's first of all, that's one thing. That's part of what we call rationalizing. So surds, any number that is a surd is irrational. It's not rational, basically. And a whole number is an example of a rational number. So, yeah, that is going to help us when it comes to rationalizing. So let's take the first example, root 2. So we know that if we have the square root of 2, we can multiply that by the square root of 2, and that will give you a number that is not a surd, i.e. rational. Okay. We can use this example to motivate us for our next one, which is this. Right. With this kind of example, the kinds of things they can ask us to do is rationalize the denominator. Now, what does that mean? It means to make the denominator rational. Rationalize the denominator. Okay. So that being said, we're going to multiply. Well, think about the previous example. The square root of 2, we multiplied that by the square root of 2, and that gave us a rational number, i.e. a number that didn't have a surd in it. So in this example, if we multiply the top number by the square root of 2 and the bottom number by the square root of 2, then the top number becomes 7 times the square root of 2, and the bottom number becomes just 2, i.e. the bottom number has been made rational. And also note that we've not changed the fraction. They're exactly the same because we've done the same thing to the top and the bottom number. So it's an equivalent fraction. Does that make sense?
Yeah.
So if I then gave you this example here, which is, let's say, 7 over square root of 3, how would I rationalize this?
You would multiply the top and bottom by root 3.
Yes, top and bottom by root 3. And then what would that give you?
7 root 3 over 3.
Yes. Okay, let's take another. Let's go 7 over the square root of 7. What then?
You would multiply both by root 7.
Okay. And that gives us,
Root 7 root 7 over 7.
okay, so 7 root 7 over 7. And we can actually simplify this one.
Would it just be root 7?
Yes, because 7 divided by 7 is 1, so you really have 1 root 7 over 1, dividing both the 7s, and then that leaves you with, well, 1 times root 7 is just root 7, root 7 divided by 1 is just root 7. So there we go. So that's one type of rationalization that we can do. Okay, now let's take this example. So pay attention to the question that we did on the first slide with the 2 minus root 3. We've got 7 over 2 minus root 3. So my question to you is, from the first example, what did we multiply 2 minus root 3 by to get a whole number?
To add root 3?
Right, so in this case, we can multiply the top by 2 add root 3, and we can multiply the bottom as well by 2 add root 3. So this becomes a double bracket expansion. So the top bit becomes, well, 7 times 2 is 14. 7 times root 3 is 7 root 3. And the bottom, well, 2 times 2 gives us 4. 2 times plus root 3 is plus 2 root 3. And 2 times minus root 3 is minus 2 root 3. And also minus root 3 times root 3 is minus 3. And then that simplifies to 14 plus 7 root 3 over 1. And then that simplifies to 14 plus 7 root 3. Does that make sense?
Yeah.
Cool. So again, we've achieved our goal of making the denominator rational. Okay, so let's suppose then I were to take this example, trying to follow the pattern. 7 over, let's say, 3 minus root 7. What do you think we'd do here?
You would multiply top and bottom by 3 add root 7.
You'd multiply top and bottom. Yes, exactly. So you're noticing the pattern here. You're doing the opposite sign. Call that the conjugate. So yeah, we multiply that by 3 plus root 7. And this also multiplied by 3 plus root 7. And then what will the top bit expand to?
21 add 7 root 7.
Yep. And then the bottom?
2, yeah, just 2.
Yeah, just 2. So how did you do it, by the way? What was your thinking for this one?
Do you mean for the bottom?
Yeah, for expanding it.
I wrote down 3 minus root 7 times 3 add root 7.
Mm-hmm.
And then I did 3 times 3, which is 9.
Mm-hmm.
Then 3 times root 7, which is 3 root 7.
Mm-hmm.
And then minus root 7 times 3,
Mm-hmm.
which is minus 3 root 7.
Mm-hmm.
And then minus root 7 times plus root 7, which is 7. Minus 7.
Minus 7, yeah. So you'll notice as well that anytime you do this kind of expansion, 3 minus root 7, 3 plus root 7, or something minus something, and then the same something but plus the other something, you always get this, the in-between terms cancelling. And this is something that we can actually use in our next examples to help us with just expanding the brackets really quickly. So with this, we get 21. With this, we get 21 plus 7 root 7, all divided by, this will simplify to 2. But as we do another example, you'll see that actually you can do this quite a lot. So let's suppose you had 2 over 1 plus the square root of 5. What could we multiply things by here?
1 minus root 5.
Yeah, so we're going to multiply this by 1 minus root 5 and multiply the bottom also by 1 minus root 5. Now, the thing that I want you to spot here is you can do the normal expansion, the long way, but we realize that the middle terms are always going to cancel in this kind of situation. It's called the difference of two squares. So the top bit will expand to 2 minus 2 root 5, but the bottom, it's just going to be 1 times 1, take away the square root of 5 times the square root of 5, which in this case is 5. Because we know the middle terms are always going to cancel. Does that make sense?
Yeah.
And then this becomes 2 minus 2 root 5, all divided by minus 4. In actual fact, we can simplify this a bit further. If I factorize the top, I get 2 open bracket 1 minus root 5, all divided by minus 4. I can divide top and bottom by 2. That gives me 1 minus root 5 over minus 2. So there we go. Okay. Could we do 1 plus the square root of 7 over 1 minus the square root of 7? So I'll give you a moment to have a go at that.
I have the answer.
Oh, okay, awesome. So what was your start process?
First, I multiplied both of them by 1 add root 7.
Yep, so times the top by 1 plus root 7, and then the bottom also by 1 plus root 7.
And for the top, I got 8 add 2 root 7.
That sounds good, yeah, because 1 times 1 is 1. 1 times root 7 is root 7. Root 7 times 1 is again root 7. Root 7 times root 7 is 7.
And for the bottom, I got 6.
Yep. 6, did you say?
Minus 6, sorry.
Minus 6, yes. Because for the bottom, we have that difference of two squares, where you could expand it the long way, or you realize that it's just 1 minus root 7 squared, which is 7, because the in-between terms cancel. So the top bit simplifies to 8 plus 2 root 7, and the bottom cancels to minus 6. We could actually go a bit further. Everything here is divisible by 2, so we can divide by 2, so it becomes 4 plus root 7 divided by minus 3. Equally, you could have factorized the top and then did it that way. So there we go. How do you feel about rationalization now?
I understand it now.
That's good. All right, let's take it a little bit further though. I just want to give you some questions that just make you think just a little bit more, or just apply your knowledge. Right, so we'll warm up first, I think. We'll warm up with 2 questions. So let's put those on the next slide. I'll give you a couple of minutes to have a go at this.
I've done the first one, but I'm doing the second one now.
Okay.
I'm not too sure how to do it though.
Well, how did you do the first one?
For the first one, I did square root of 12 squared times root 30 squared.
Okay, so here we see if I lay it out sort of the long-ish way, I'd say x squared is equal to the square root of 12 squared plus the square root of 30 squared. So x squared equals the square root of 12 squared is just 12, and the square root of 30 squared is 30. So x squared is indeed equal to 42. So therefore, x equals the square root of 42. Can this be simplified in any way? No, because 42 is just 2 times 3 times 7. Yeah, that doesn't simplify. And then does that make sense? Did you do it this way as well?
I did multiply by accident.
Oh, okay. So Pythagoras' theorem adding. Well, it's all good. It's probably been a while since you've done Pythagoras, I'm guessing.
Yeah,
Yeah. Okay.
I think I have the answer.
Awesome. Okay. Give me one moment. I'm just gonna put some questions on the board. Okay. So, go on. How did you do the second one?
In the second one, I did 200 add x squared equals 300.
Nice. Yes. So setting up Pythagoras' theorem, the longest side is the hypotenuse. So the square root of 200 squared plus x squared equals the square root of 300 squared. And you said 200 because the square root of 200 squared is 200 plus x squared is equal to 300. Yep.
And then I did 300 minus 200,
Mm-hmm.
which was x squared equals 100, and then
Mm-hmm.
I did the square root of 100 is x.
Which is 10. Nice. Okay, so warming up a little bit more. On the next slide, we've got the questions that say find the perimeter of each of these rectangles. So I'll let you have a go at those. If you can, could you simplify your answers as much as possible?
Okay. I think I have the answers.
Awesome. Okay, so the first
For
one.
the
Mm,
for the first one, I got 375 centimeters.
375. I feel like I'm. Go on. What did you do?
I first did 100 times 3.
For the perimeter,
I did the questions wrong, I think.
what did you do?
For the first one, I did 10 root 3 squared instead of times 2.
Ah, okay. Should I give you some more time to try and fix it?
Yeah, yes, please. I have the answer for the first two, but for the last one, I'm not too sure.
Okay, awesome. So, um, right, for the first one then,
For
what
the
mhm.
first one, I got 30 add 4 root 3.
That 30 add 4 root 3.
Yeah,
Okay, so how did you do that one?
I did um 2 times 10 root 3.
Okay, because you have two of them. And two, wait, you did what, sorry?
2
Yeah.
times 10 root 3.
Okay, yeah, 2 times 10 root 3.
And add 2 times 5 root 3.
Okay. And what is 2 times 10 root 3?
I got 20 add 2 root 3.
Ooh, but 10 root 3 is one thing stuck together. So 2 times 10 root 3 is in actual fact 20 root 3.
For the other one, it would be 10 root 3.
Mm-hmm.
So then 20 root 3 add 10 root 3,
Mm-hmm.
which is 30 root 3.
Yeah. So, okay. And then the next one.
The next one I did 2 times root 10 add root 2.
Okay, so two lots of root 10 add root 2, which gives what? Yeah.
Add 2 times root 10 minus root 2,
Yeah.
which gives me, for the first one, 2 root 10 add 2 root 2.
2 root 10 add 2 root 2. Yeah.
And for the other one, it's 2 root 10 minus 2 root 2.
Mm-hmm.
And then I added them together to give me 4 root 10.
Yes. Nice. And then for the last one, well, with the last one, we have to, well, to make it easier for ourselves, if we change the square roots 72 and the square root 18 to something a bit easier, we can then add them easily. So the square root of 72 can be written as the square root of 36 times the square root of 2. And then that is equal to 6 root 2, because the square root of 36 is just 6. Equally, with the square root of 18, that can be written as the square root of 9 times the square root of 2. And that's 3 root 2 because the square root of 9 is 3. And then now we've got terms that we can add together really nicely. So we've got 6 root 2 over here, and we've got 3 root 2 over here. So we've got 2 lots of 6 root 2 plus 2 lots of 3 root 2. 2 lots of 6 root 2 is 12 root 2, and 2 lots of 3 root 2 is 6 root 2. And then adding those together, that gives us 18 root 2. Does that last example make sense?
Yeah.
Cool. Okay. And our next thing then of working out. Yeah. Oh, this one's a good one. Okay, well, first of all, let me ask you this question. So imagine you don't have a calculator. Actually, before we get to that one, how would you work out the area of these rectangles on slide 7?
You would multiply, for the first one, you would do 10 root 3 times 5 root 3.
Yep. And we've got to be very careful how we do this one. How do we approach that?
We would do 10 times 5
Mm-hmm.
root 3, which is 50 root 3.
Okay, that's where you've got to be really careful. So there's 10 times 5, which is 50. But you've got root 3 that appears twice. So you've got root 3 times root 3, which is 3. So in actual fact, it's 50 times 3. Let me just make that extra clear, actually. This is the same thing as 10 times root 3 times 5 times root 3. I can reorder this. I get 10 times 5 times root 3 times root 3. Is that making sense so far?
Yeah.
And then I have 10 times 5, which is 50, and then root 3 times root 3, which is 3. And then that gives you 150. The final answer for this one is 150 centimeters squared. Okay. And then the next one?
The next one you would do root 10 add root 2, times root 10 minus root 2.
Yep. Root 10 add root 2 times root 10 minus root 2. Oh, this looks like one of those ones that we were doing before when we were rationalizing the denominator. Do you remember the quick way of expanding this?
Root 10 times root 10,
Mm-hmm.
which is 10, and then 10 minus 2.
Yeah, that's what the final answer is going to be. So, yes, root 10 times root 10, which gives you 10. Root 2 times minus root 2, which is minus 2. Because the other terms in between are going to cancel when you expand it the long way. And of course, if you wanted to check, you can just do it the long way and you'll see that it will give you the same answer, which is 8. So this one is 8 centimeters squared. And then this last one,
The last one you do root 72 times root 18.
right? How can we make this easier for ourselves?
We can make it 6 root 2 times 3 root 2.
Nice, because on the previous example we've done that, but just to show it again, square root of 72 is square root of 36 times the square root of 2. Square root of 18 is square root of 9 times the square root of 2. This simplifies to 6 square root of 2, and this simplifies to 3 square root of 2. 6 times 3 is 18. Root 2 times root 2 is 2. So that gives us 36. So 36 centimeters squared. Cool. Last question, or last kinds of questions, is this. I've got two numbers. Out of these two, which is bigger? I imagine you don't have a calculator for this.
Would it be 3 root 5?
Why?
Because you're multiplying the result by 3, and the first one is by 2.
But equally, the first one is the square root of 7, but the other one's square root of 5. So root 5 is smaller than root 7. So how can we be sure?
I'm not too sure.
Well, do you know how we can simplify surds by rewriting them? What about unsimplifying surds? How might you unsimplify?
For the first one, would it be root 4 times root 7?
Yes. The square root of 4 times the square root of 7. And what does that become?
28.
The square root of 28. And then the second one?
It would be root 9 times root 5,
Yes. And that becomes?
which is root 45.
Yes. And then with that, you have a much more convincing argument that the right-hand side is the bigger one. Does that make sense?
Yeah.
Cool. So with that, I can leave you with this question to have a go at. I'm going to leave it unanswered. Let me know your thoughts over the week with that question there. And in terms of rationalizing the denominator, I think these are some good questions to answer just to keep the practice up. We've got the rationalizing and we've got this ribbon question as well. But now overall, how do you feel?
I understand them more.